In this video, we solve a second order differential equation by finding two linearly independent series solutions centered at t naught equals 0, which is an ordinary point of this differential equation. We're asked to compute the first 5 non-zero terms of the corresponding series and indicate the interval on which they are guaranteed to converge. This is a problem from the Constanda differential equations text. I actually really love this book, Differential Equations, a Primer for Scientists and Engineers. And this is the first edition. I think they're on the second or third edition already. But I think that this is a great example. Now, this is our second example. So I'm going to show less of why we're doing what we're doing. I'm going to do a little bit less explanation, and I'm just going to work through the method. This is probably what you will do if you are solving a differential equation using the series solution method on a quiz or a test. So there's a little bit less explanation about why we're doing what we're doing, but we're still going to go through all of the steps and solve this from first principles. So the first thing that I would do is I would distribute that y double prime and the y to these binomial expressions. So we'll have t squared times y double prime plus y double prime minus y prime plus t times y minus y equals 0. And here we are looking for two linearly independent series solutions centered at t equals 0. T naught equals 0 is an ordinary point because that leading coefficient is equal to 1 when t naught equals 0, not 0. So that makes it an ordinary point rather than a singular point. So we're going to let y equal the sum as n goes from 0 to infinity of c sub n times t to the n, since t is our independent variable. And then we're going to compute the first and second derivative from here. We're assuming that this is the form of our solution. We just need to find the right values of those constants, c sub n. So if that is my solution, the derivative of that is the sum as n goes from 1 to infinity of c sub n times the derivative of t to the n, which is n times t to the n minus 1. We're just taking the derivative term by term in that series. Actually, let's say and. Derivative of this guy, we're going to start with n equals 2 here. We increase that index by 1 every time because the derivative of the constant term in this series is 0 in this series. And then we bring that n down and we take the derivative of t to the n minus 1, which is n minus 1, t to the n minus 2. Okay, so now you've got these guys. We're going to substitute into the differential equation. You have 1, 2, 3, 4, 5 terms. So we're going to have 5 series that we need to add together over here. So we're assuming that y is a solution. So if y is a solution, these series will satisfy this differential equation. So the equation becomes this, that t squared times y double prime plus y double prime and then we're subtracting y prime. And then we are adding t times y. And y was the sum as n goes from 0 to infinity of c sub n times t to the n. And then we're subtracting y itself. Okay, so we've got 5 series that we need to add together in order to find the values of those coefficients. So the first thing I would do is I would distribute that t squared into this series and that t into this series. Multiplying every term here by t squared just results in adding 2 to that exponent. Just using our exponent properties, t to the second times t to the n minus 2 is t to the 2 plus n minus 2. So that's going to be a t to the n after you're done. You leave everything else alone. This one we're not doing anything with, so I'm just going to rewrite it. Same there. And here when I distribute that t in, that's going to be a sum as n goes from 0 to infinity of c sub n, which is a constant, and I've got t to the n times t to the first, which is t to the n plus 1. And then you've got this. Okay, so we've got 5 series and we want to add them together so that we can find the values of the constants. In order to do that, all the series need to start with the same power of t. So we need to think about where these series start. So if I plug in n equals 2 to this, we see that this starts with a t squared term. If you substitute n equals 2 to that, 2 minus 2 is 0, so that's going to start with a constant term, a t to the 0 term. When n equals 1, that's t to the 0 as well. Then here, when n equals 0, we have t to the first. And then this one starts with a t to the 0 term. Okay, so we do that. We figure out which term each of these series are starting with so that we can remove terms from all of the series as necessary so that they all start with the highest power of t on this list. So this one starts with a t squared. That's the highest power of t. So I need all 4 of these to start with a t squared as well. So this one starts with a constant term. So I'm going to take out the constant term and the t to the first term from here and here. On this one, I just have to take out the t to the first term. On this one, I've got to take out 2 terms, the t to the 0 term and the t to the first term. So we're going to remove, let's say, 2 terms from the second, third, and fifth series, and 1 term from the fourth series, so that the resulting series all begin with a t squared term. And again, the reason why we do that is because we want to collect like terms. We want to be able to add 3t squared from this one to 5t squared from that one, just for example. But in order to do that, we have to have them all starting at the same place. So this one already starts with a t squared, so I will leave it alone. That one starts with a t to the 0 term. So when n equals 2, we get c sub 2. Times 2 times 2 minus 1, which is 2, times t to the 0. So that's our constant term. And then we need a t to the first term. So that's going to come from substituting the next value of the index. We took care of n equals 2. So now we want to substitute in n equals 3. So we'll have c sub 3. And then we'll have 3 times 2, which is 6, times t to the first. And then the next term will be a t squared term. So that's going to stay in the series. We took out the n equals 2 and n equals 3 terms. So the rest of the series starts with n equals 4. And otherwise it looks exactly the same. So you're just going to write down c sub n times n minus 1 times t to the n minus 2. Okay. Similarly, we're going to do the same thing here. Starts with n equals 1, so we're going to take out the n equals 1 term and the n equals 2 term because it starts with a t to the 0. And then the rest of the series is going to start with n equals 3. So let's see, when n equals 1, we have 1 times c sub 1 times t to the 0. When n equals 2, you've got c sub 2 times 2 times t to the 2 minus 1, which is t to the first. And then the rest of the series starts with n equals 3. So I guess that should kind of be moved up there. And otherwise, it's going to look exactly the same. So this is our first series. This is our second series that we have rewritten in this new way. This was our third series. We've got 5 of them, so we need to do the same thing to this one and this one. That's our fourth series. It starts with a t to the first term, so I just want to take out the t to the first term so that the resulting series starts with t squared. And the t to the first terms comes from letting n equal 0. So we're going to add c sub 0 times t to the first. And then we pick up where we left off. That's the n equals 0 term. The rest of the series starts with n equals 1. Oh, that's n plus 1. So this is our fourth series. And I'm going to write plus dots because I want to continue this on the next page. We need to add in that last series, which starts with a t to the 0. So we'll have to take out 2 terms from that. Okay. When n equals 0, you have c sub 0 times t to the 0. When n equals 1, got a negative c sub 1 times t to the first. And then the rest of the series starts with n equals 2. And otherwise looks exactly the same. And all of that combined is equivalent to our original fifth series. Okay, so now these series all start with a t squared. If you plug in n equals 2 to that, you get t squared. N equals 4 to that, you get t squared. N equals 1 to that, you get t squared, and so on for all 5 of them. But they don't look the same. We want all the exponents to match. So we want to rewrite these series so that they all have a matching exponent. So I'm going to look at the exponents that I have and see which one occurs the most often. I've got a t to the n, a t to the n minus 2, a t to the n minus 1, a t to the n plus 1, and a t to the n. So I've got 2 that are t to the n's. So I'm going to make these 3 look like this t to the n. It's going to have that same form so that we can collect like terms. That's necessary so that we can add those series together. So what we'll do for these series, these 3, is we'll take the exponent we have, so that's n minus 2, and we're going to set it equal to the exponent we want, but I can't let n minus 2 equal n. So instead of letting it equal n, I'm going to change that variable. I'm going to call that k. So if n minus 2 is equal to k, then n is equal to k plus 2, and so we can write this series in terms of k. So it's just telling us to start counting at a different place, but as we go through that count, we're still going to end up with the same terms in this series. Here I'm setting the exponent I have, n minus 1 equal to the exponent I want, that's k, and I'll solve for n as well, so I'll have k plus 1 here. And on this one, I'll take the exponent I have, the n plus 1, set it equal to k, and then solve for n. Okay. And then for these 2 guys, I'm just going to rewrite them with n equal to k. So I'm just changing out the letters. So we are now taking that second step to add these series together. We're relabeling the indices. So that the exponents have the same form. That's going to allow us to add these series together. Okay, but first I want to collect all of my constant terms together. So I'm going through this list and I'm looking for my constant terms. So there's one, I've got 2c sub 2. And there's one, I've got negative c sub 1. That's a t term. There's another constant term, negative c sub 0. So that's that there. And then we're adding the t terms next. I've got a 6c sub 3 times t, just factoring out that t for right now, minus 2c sub 2 times t, plus c sub 0 times t, minus c sub 1 times t. Okay, and then you've got these 4 series or 5 series that are left. This one, this one, this one, this one, and this one. So we're just going to rewrite those series here. And I think I'm just going to write them vertically to make my paper a little bit neater. So first I'll write the first series over again. This is the sum as k goes from 2 to infinity of c sub k times k minus 1 times t to the k. That's our first series. The second one is this one. When n is equal to 4, k is equal to 4 minus 2, so k would start at 2. And then here, you just replace all of the n's with k plus 2's. So you're going to have c sub k plus 2 times k plus 2 times k plus 1 times t to the k. That's my second series. Now for the third series, we're right here. This one starts with n equals 3. When n equals 3, k is equal to 3 minus 1, which is 2. And we're going to replace all the n's with k plus 1's. So that's c sub k plus 1 times n, which is k plus 1, times t to the k. Then here, we need to write that one in terms of k as well. When n is equal to 1, k is equal to 1 plus 1, which is 2. So I'm focused on this one now. And n is replaced by k minus 1. So this is c sub k minus 1 times t to the k. That's our fourth series. And then our last series is this one. You're just replacing n with k. So I'm just going to write that on this line. Okay, so I've got this term plus this term, just a constant times t. And then all of these start with t squared. When k is equal to 2 for each of them, we have a t squared term. When k is equal to 3, we got a t cubed term. When k is equal to 4, we'll have a t to the 4th term. So we can add these together now. By removing those terms from the series, we were able to get them to all start with a t squared term. And now they match, they look the same. So it's very obvious that when k equals 2, that all of these start with a t squared. So now we can collect like terms. We're going to add the series together. So I've got 2 times c sub 2 minus c sub 1, minus c sub 0, plus 6c sub 3 minus 2c sub 2 plus c sub 0 minus c sub 1 times t. And then we're adding all those series together. So I'll just start with k equals 2 and go to infinity. And basically what I'm going to do here is I'm going to factor out a t to the k. So I'm going to write this, and this, minus this, plus this, minus that. And wherever I have an opportunity, I will sort of collect like terms as well. I've got a c sub k here and a c sub k here. So this I can think of as c sub k times k squared minus k, minus 1 more c sub k. So that's c sub k times k squared minus k minus 1 times t to the k. So that took care of our first series and our last series. And then I want the other ones. So I have c sub k plus 2 times k plus 2 times k plus 1. times t to the k. And we want the next one. Don't forget that sign, that minus out there. And then the last one. All of this times t to the k is equal to 0. Okay. So now we're here and we're thinking of this 0 as an infinite series with a bunch of zeros in it. So 0 plus 0t plus 0t squared plus 0t cubed plus 0t to the fourth and so on. So the only way that this series on the left-hand side is equal to this series with infinitely many zeros on the right-hand side is if all of the coefficients of t on this side are equal to 0. So we're going to set the coefficient of t to the n on the left-hand side equal to the coefficient of t to the n on the right-hand side, which in this case is 0. So our constant must be 0. And this constant multiplying the t must be 0 as well. Because we've got 0t. And then this must be 0 for k equals 2, 3, 4, and so on. Now, once you've done that, you want to take each of these equations and you want to solve for the coefficient with the largest subscript. What that will allow us to do is it will allow us to write the expression for all of the coefficients in terms of coefficients with smaller subscripts. So we're going to be able to get c sub 2 in terms of c sub 1 and c sub 0 here by just adding these to both sides and then dividing by 2. So c sub 2 is 1/2 of c sub 1 plus 1/2 of c sub 0. And then now that we know that c sub 2 is this in terms of c sub 1 and c sub 0, we can also get c sub 3 in terms of c sub 1 and c sub 0. So according to this, c sub 3 is, well, it's what you get when you add these guys, or add or subtract as necessary to get those on the other side. So we'll have 2c sub 2 minus c sub 0 plus c sub 1. We're just adding these guys, subtracting that one, and then we'll divide all of them by 6. So that's 1/3 times c sub 2, but c sub 2 happened to be 1/2 c sub 1 plus 1/2 c sub 0. And then we're subtracting 1/6 c sub 0 and adding 1/6 c sub 1. So we end up with 1/6 c sub 1 plus 1/6 c sub 0 minus 1/6 c sub 0 plus 1/6 c sub 1. Those guys reduce. We end up with 2/6 c sub 1, which is the same as 1/3 c sub 1. Okay, so we've got c sub 2 in terms of c sub 1 and c sub 0, and we've got c sub 3 in terms of c sub 1. Now, those are the coefficients of the constant term, that t to the 0 term, and then we've got the coefficient of the t to the first term, and then we had that recurrence relation. You've got c sub k times k squared minus k minus 1 plus c sub k plus 2 times k plus 2 times k plus 1 minus c sub k plus 1 times k plus 1 plus c sub k minus 1 equals 0 for k equals 2, 3, 4, and so on. Okay, again, we want to solve for the one with the highest coefficient. K plus 2 is the largest coefficient on that list. It's bigger than k plus 1, k minus 1, and of course k. So we want to get this guy by itself. In order to do that, we're just going to subtract this from both sides, add that to both sides, and subtract that from both sides. So we'll have minus c sub k times k squared minus k minus 1 plus c sub k plus 1 times k plus 1 minus c sub k minus 1. So move those over, and then we're dividing each of those by k plus 2 times k plus 1. And you could divide the whole thing by k plus 2 times k plus 1 if you want to. That's fine. That's an option for you. I decided to divide each term by that because then the k plus 1s would reduce right there. So this is true for k equals 2, 3, 4, and so on. Now we want 5 linearly independent, or excuse me, 5 terms of each of those 2 linearly independent series solutions to the differential equation. And that means we're looking for 5 terms that depend on c sub 0 and c sub 1, and 5 terms that depend on c sub 0, sorry, and 5 terms that depend on c sub 1. So we've already got the automatic c sub 0 and c sub 1 terms. And then we've got another one that depends on c sub 0 and c sub 1, and a third that depends on c sub 1. So we want to substitute in values of k to this expression here until you've got 5 coefficients total that depend on c sub 0 and 5 total that depend on c sub 1. And since c sub 1 and c sub 0 are automatic in the definition of that, the form of that solution, we really just need 4 more than the constant term and that coefficient of t to the first in the original series. So I've got 2 for c sub 1 so far, and then 1 for c sub 0. I need 2 more for c sub 1, and then 3 more for c sub 0. Okay, let's keep going. So we're just going to evaluate this expression until we have all of those, and then we'll substitute into the form of the solution to the differential equation. Easy breezy. We're going to let k equal 2 here, and that's going to give us c sub 4. So you'll have c sub 4 equals negative c sub 2 times, if k is 2, 2 squared is 4, 4 minus 2 is 2, 2 minus 1 is 1, all divided by k plus 2 times k plus 1, so it's going to be a 4 times a 3. And then we'll have c sub k plus 1, so that's 3, over k plus 2, which is 4, minus c sub k minus 1. When k is equal to 2, that's going to be c sub 1 over 4 times 3. Okay, so we've got negative 1/12 of c sub 2, which we know already in terms of c sub 0 and c sub 1 is this. So we're going to substitute that in. And you're adding 1/4 of c sub 3, and c sub 3 was 1/3 c sub 1. So you've got that there. And then you're subtracting 1/12 of c sub 1. Those actually reduce. Okay, so those guys are gone. Let's see what we get over here. I've got negative 1 over 24 c sub 1 minus 1 over 24 c sub 0. Okay, so I've got 1 more for c sub 0 and 1 more for c sub 1. Now let's evaluate at k equals 3. Again, we're substituting right here. So I have minus c sub 3. 3 squared minus 3, that's 9 minus 3 is 6. 6 minus 1 is 5. Over 5 times 4 plus c sub k plus 1. So that's c sub 4 over 5 minus, when k is equal to 3, that's going to be c sub 2 over 5 times 4. Okay, so the 5's reduce here, and you have a negative 1/4 of c sub 3. And c sub 3 happened to be 1/3 of c sub 1. And then here, bring the 1/5 down, and then you want to substitute in c sub 4, which was this. And then you're subtracting 1 over 20 times c sub 2, and c sub 2 was 1/2 of c sub 1 plus 1/2 of c sub 0. Okay. So we just need to simplify now. Negative 1 over 12 c sub 1 minus 1 over 120 c sub 1 minus 1 over 120, c sub 0, minus 1 over 40, c sub 1, minus 1 over 40, c sub 0. So I want to combine all the c sub 1 terms together and the c sub 0 terms together. So I've got negative 1/12 times c sub 1. Then I've got minus 1 over 120 times c sub 1 and minus 1 over 40 times c sub 1. Now if I want to, oh, I'm sorry. I was looking at my paper and I was not looking at the camera, so I didn't realize you guys couldn't see that. But I'm just collecting like terms in the c sub 1. So I've got this one, and this one. I want to add those together. That means we need a common denominator. So it looks like the common denominator is 120. So we end up with, so I'm multiplying here by 10 over 10. So I've got negative 1/10 over 120 minus 1 over 120. So that's negative 11 over 120 minus 3. So negative 14 over 120 now times c sub 1. For the c sub 0 terms, you've got negative 1 over 120 minus 1 over 40. When multiplied by 3 over 3 there. So we have minus 1 minus 3 is negative 4 over 120 times c sub 0. Okay, now this one can be simplified further. Divide the numerator and denominator by 2. Here we can divide the numerator and denominator by 4. And we get that. I think we might have enough coefficients. Let's see. We needed 4 more that depend on c sub 0 and c sub 1. So I've got 1 that depends on c sub 0, and then 2 that depend on c sub 0, 3 that depend on c sub 0. I need 1 more that depends on c sub 0. And c sub 1, I've got 1 there, 1 there, 1 there, and 1 here. So I've already got 4 for c sub 1. I just need 1 more that depends on c sub 0. So we need to substitute again. Let's let k equal 4 this time. That's going to give us c sub 6. And we're still substituting into this equation right here, this recurrence relation. So when k is equal to 4, we get c sub 6 equals negative c sub 4 times 4 squared is 16. 16 minus 4 is 12. 12 minus 1 is 11 over. When k equals 4, it's going to be 6 times 5 plus c sub 5 over 6 minus c sub 3 over 6 times 5. Okay, and then we just substitute c sub 4, c sub 5, and c sub 3 in here in terms of c sub 1 and c sub 0 and simplify. So we've got negative 11 over 30 times c sub 4, which is negative 1 over 100, or negative 1 over 24 minus 1 over 24 times c sub 1 and c sub 0 respectively. That's c sub 4. And then we want to add 1/6 of c sub 5, which is this. So you have negative 7 over 60 times c sub 1 minus 1 over 30 times c sub 0 minus 1 over 30 times c sub 3. And c sub 3 was 1/3 of c sub 1. That was on the last page. Okay, so that is our result. I think I'm just going to use a calculator for the arithmetic because we're taking differential equations and I don't want to have an arithmetic lesson at this point. So we've got 11 divided by 30 times 24. Well, I guess I could have done that one in my head. So that's 11 over 720 times c sub 1 minus 11 over 720 times c sub 0. And then over here we have minus 7 over 360 c sub 1 minus 1 over 180 times c sub 0 minus 1 over 90 times c sub 1. And then we want to grab all the c sub 1 terms. And then we want to grab the two c sub 0 terms. And you want to add those fractions. We could get a common denominator, but again, I'm just going to save a little bit of time by using the calculator for the arithmetic. So I've got negative 11 over 720 times c sub 1, and then over here, negative 11 over 720 minus 1 over 180. So that's, oops, negative 1 over 48, apparently, after simplification. Okay, great. So now we've got enough coefficients in terms of c sub 0 and c sub 1 that we are ready to substitute into the form of the solution. Notice that we went up to c sub 6, so we want to write down our solution going all the way up to c sub 6 times x to the 6th. Yeah, so these types of problems take a long time. Take a little longer when you're explaining it. But when n equals 0, we have that constant term. When n equals 1, we get c sub 1 times t to the first. When n equals 2, we've got c sub 1, or c sub 2 times t squared. Remember the subscript here and the power of t match. So when n equals 3, we have c sub 3 times t cubed, c sub 4 times t to the fourth when n equals 4, plus c sub 5 times t to the fifth when n equals 5, c sub 6 times t to the sixth when n equals 6, plus higher order terms or higher degree terms. Degree if the coefficient is non-zero, order otherwise. Okay, so now we just want to substitute everywhere that we can for these coefficients. C sub 0 and C sub 1 we're going to leave alone. But C sub 2 from earlier was, let's see, it was 1/2 C sub 1 plus 1/2 C sub 0. So we're going to substitute that in for C sub 2. And then I want to substitute in for C sub 3, which was 1/3 C sub 1. And that gets multiplied by t to the third. And then we want c sub 4 times t to the fourth. So you've got negative 1 over 24 times c sub 1 minus 1 over 24 times c sub 0 plus the coefficient of t to the fifth, which is c sub 5. So you have negative 1 over 60 c sub 1 minus 1 over 30 times c sub 0 plus the coefficient of t to the sixth, which is c sub 6, which happened to be a negative 11 over 720 minus 1 over 48 times, that's c sub 0. And I'm sorry, earlier when I was writing, it looks like I started writing 1 here when I meant to write 0. So if your notes are wrong, sorry about that. Okay. So that is our series solution. Now that includes 2 linearly independent series solutions. To find the 2 linearly independent solutions, we're going to group the terms that involve c sub 0 and group the terms that involve c sub 1 and then factor out those constants. So first I will focus on the c sub 0 terms. I've got one of them, another one, and then another one, and then another one, and then the last one. So I've got 1 times c sub 0 there, 1/2 t squared times c sub 0. Then you've got a negative 1 over 24 times t to the fourth times c sub 0 minus 1 over 30 times t to the fifth there. And then we have minus 1 over 48 times t to the 6th there. Plus higher degree terms. And now we're going to collect the terms involving c sub 1. So I've got a c sub 1 term here, and here, and here, and here, and here, and here. That's c sub 1 times t. This is c sub 1 times 1/2 t squared. This is 1/3 times t cubed times c sub 1. This is negative 1 over 24 times t to the 4th times c sub 1. And we've got minus 7 over 60 times t to the 5th. And that would be our 5 terms, but we've got one more. Might as well write it down. So we've got negative 11 over 720 times t to the 6th times c sub 1. So that is our general solution. We've got 2 linearly independent solutions to this differential equation. If we multiply them by constants, c sub 0 and c sub 1, and add them together, we have the general solution. Now the last part of the question says, indicate the interval on which the series in this solution are guaranteed to converge. In order to find that interval, we're just going to take this and divide by t squared plus 1. So our differential equation will look this way. Got y double prime minus y prime. We're dividing by t squared plus 1. That was our leading coefficient. Now, in order to determine where these two solutions are guaranteed to converge, we need to look at the coefficient of y prime here and the coefficient of y there, and think about where those are well defined. Now, typically, if we were in calculus 2 and we were finding the interval of convergence for a negative 1 over 1 plus t squared, we would say that kind of looks like a over 1 minus r. R must be negative t squared. That will, the geometric series centered at t equals 0 will converge whenever the negative t squared, absolute value of negative t squared is less than 1. And so we'd say that t has to be between negative 1 and 1. That's what we get here, and we would have exactly the same a result over here as well. But in Dr. Constanda's book, he says that we just need to look at that denominator. He says the interval is going to start at t equals 0, and then it's going to go out from t equals 0 to the nearest singular point. And it turns out that 1 plus t squared is never equal to 0, not in the real number system. So based on that, we're going to say this function is analytic for all real numbers, and this function is analytic for all real numbers. Although I trust Dr. Constanda, but my training from calculus 2 makes me wonder, I'm like, why is that guaranteed to be analytic outside the interval from negative 1 to 1? I would think that you would still have issues outside the interval from negative 1 to 1 because of what we know about geometric series and the geometric series representation of that. So based on Dr. Constanda's rules, the interval of existence here is negative infinity to infinity because that denominator is well defined for all values of t. So we would say that these series solutions are guaranteed to converge on this interval. But I don't know, there's some part of me that wonders about this series, or the power series representation for this, which can be written this way. If we have that as a over 1 minus r, we could call this the sum as n goes from 0 to infinity of a times r to the n. This series will converge to this function when the absolute value of r of t, which is the absolute value of negative t squared, is less than 1, which means that the absolute value of t squared is less than 1. And that means that the absolute value of t is less than 1, which means that t is between negative 1 and 1. So my intuition tells me that this would be the interval of existence. But if Dr. Constanda says that we don't have to worry about this, that the fact that this is well defined for all values of t means that this function, negative 1 over 1 plus t squared, is going to be analytic for all values of t, then the interval of existence is this. But I'm thinking it might be this, but I must be wrong because Dr. Constanda is not wrong about things like that. I need to talk to him and make sure that I understand why this interval of existence is what it is. But according to his discussion, that's the interval of existence. And I am wondering myself, why? Why isn't it that? Maybe you're wondering too.